The presentation of November 18th was affected by several technical problems, so we are recording the presentation again. Before starting, I would like to thank everybody who stayed with me that night. But now let's jump on the Webb Space Telescope and start to explore the secrets of planet and star formation. Our eyes see the universe through a very narrow range of colors that compose the visible light. However, the sun, the other stars, and distant galaxies emit much more light than what we can see with our eyes. Together, all the components of the light are called the electromagnetic spectrum. Under many aspects, the light behaves like a wave. And so there are a series of peaks and valleys that are following each other on a regular rhythm. Phenomena that are characterized by very high energy and at very high temperatures usually emit most of their light in the gamma ray, X-ray, or ultraviolet. And the separation between the various peaks are very narrow. As we move to our lower energies or lower temperature, the maximum of the light moves toward the infrared, the microwave, and the radio waves. And the separation between the peaks becomes broader. We'll see later that this is a very important aspect for understanding the universe. The Webb Space Telescope is going to look at the universe at colors that are very different from what we can see with our eyes. It can see the reddest part of the visible light here, but it is also very sensitive in the infrared, in the near infrared, and in the mid-infrared. Because of its sensitivity, everything that is on Earth becomes very, very bright for Webb. In fact, everything that has a temperature around 50, 100 Fahrenheit degrees shines in the infrared. So we have to protect Webb from the radiation not only that is coming from the sun, but also the radiation that is coming from the Earth and the Moon. And we have to cool down the telescope. Otherwise, even Webb would be so bright that it would outshine the radiation that is coming from the other stars and distant galaxies. Because of this reason, we are going to put Webb at 1 millionth mile away from the Earth, on the opposite position from the sun. The location where Webb is going to stay is called the second Sun-Earth Lagrange point. And this is a very special point where gravitational pull from the Earth and the sun balance the centrifugal force that would make Webb run away. In L2, Webb is going to rotate around the sun at the same rate as the Earth. And so 1 year for the Earth, so the Earth will finish one rotation around the sun in 1 year, and the same will happen for Webb. As it's rotating around the sun, Webb is also rotating around L2. And in doing so, is always showing the solar panels that are used to recharge its battery to the sun. Webb is equipped with a big umbrella that is called the sun shield, and it is this diamond-shaped structure, and is always showing that diamond-shaped structure to the sun to protect its science instrument. The observing side, where there is the primary mirror that consists of 18 hexagonal golden coated mirrors, the secondary mirror, and the science instruments are all kept at negative 400 Fahrenheit, while the side that is facing the sun is at 260 Fahrenheit. So there is more than 660 Fahrenheit degrees in difference between the sun-facing side and the observing side. This difference in temperature is achieved using the sun shield. The 5 layers that constitute the sun shield are very effective in dispersing the heat and in cooling down the telescope. We decided to face all the challenges needed to put in space a telescope as big as a Webb that observe in the infrared because we have 4 main scientific questions that we want to answer. The first one is understanding how the first stars and galaxies look like. To do that, we are taking advantage of the specific phenomenon that is called the Doppler effect. As an object moves toward us, as a wave moves toward us, the wave compresses. And when it moves away, if the object moves away, the wave that is emitted by the object stretches. We experience that, for example, if something is moving toward us or moving away. The light does the same thing. As the universe expands as a consequence of the Big Bang, the separation between the galaxies increases, and the light that was emitted initially by a galaxy that was coming from very hot stars and therefore was very blue stretches to a longer wavelengths that are visible first in the optical, and then they stretch and arrive to the near infrared and mid infrared. This is the phenomenon that allow us to see the very distant galaxies that are 10 or more billion years away from us. The other reason why we wanted a very big infrared telescope, it's because we want to see how the universe evolved after the Big Bang to become what we see nowadays. If we look at some of the deepest images ever collected, for example, by the Hubble Space Telescope, we see that nearby galaxies tend to be big and they have very regular shapes. They are either ellipticals or big spirals. However, as we start to look deeper in these images to more distant objects, we are also looking at a universe that is much younger than what we see today. And the galaxies there become considerably more irregular. They have irregular shapes. They also show evidence for collisions. And then the very early galaxies are very small and not very well defined. So nearby galaxies are mainly spirals and ellipticals. As we move at the intermediate universe, we see that they become more irregular and they often tend to be close to other galaxies and interacting with these galaxies. And then the very distant galaxies are very small and compact. We want to see with Webb how this evolution occurred when the galaxies started to build up their various structures. For example, we see already that 3 billion years ago, the galaxies that are 3 billion light years away from us have already developed very well-defined spiral structures, and they have a bright core that is called bulge in the center. These structures seem to remain in place as we move backward to around 9-10 billion years ago. To understand when these structures grew up exactly, we need to have a much better resolution than what Hubble can provide us. Here you see, for example, a comparison between a galaxy that was similar to, for example, the antennae, if it were at the distance of 10 billion light years from us, seen with Hubble, and on the right, seen with Webb. These are, of course, simulations. We haven't launched Webb yet. But the resolution of Hubble that allow us to understand the various structures is 1,300 light years, while with Webb, we can look down to 800 light years. And this is an incredible progress because we can understand that some of these structures, like this bright point here, is actually real and not just, it's much smaller than what we were seeing in this other image. In those small bright spots in these distant galaxies, we have an episode of tremendously active star formation. For example, what you see here is a collage of Hubble exposures that are mapping the entire Tarantula Nebula. This image is roughly 800 light years in diameter. And in these regions, there are at least 3 star clusters that formed with just few million years one from the other. There are also large arches of dust and gas, and there are big cavities that were created by the explosion of very powerful supernovae. At the edges of these arches and these cavities, there are also new episodes of star formation with stars that are forming right now. And this image is extremely large. There are 400 million pixels in this image. And so you do not appreciate the richness of how many stars there are here. But in these details of the center of the image, you can see that in very compact regions that are just a couple of light years away, we can find sometimes thousands of stars that are 100 times more massive than our sun, or 10 times smaller than our sun, and they're all coexisting together. So to understand the images that we see at high redshift with Hubble and Webb, we need to really understand the cycle of the stars by looking at nearby region of star formation. Infrared observations are extremely powerful to understand region of star formation because dust tend to permeate this region and hide the stars that are forming right now. What you see here is one of the most iconic images that Hubble ever took. This image was taken initially about 20 years ago with the Wide-Field Planetary Camera 2, and then it was taken again a few years ago using the most advanced camera that Hubble ever had, the Wide-Field Camera 3. The Wide-Field Camera 3 can see in the optical, where we can see these huge columns of dust and gas that are called the pillar of creation. At the top of these big columns, we think that there are stars that are forming. However, we cannot see these stars in formation because they are completely wrapped around their dusty cocoon. Also, the image doesn't show many stars. There are just few bright pinkish sources in the background. However, the Wide-Field Camera 3 can also see in the near infrared. And when we look at this region in the near infrared, a multitude of stars in the background appear. These are the stars that belong to the disk of the Milky Way, but also we can see the stars that are forming at the top of the pillars. And we can see through the thick, dark column of dust to see that their structure is complex. Some parts of the columns are not very dense, and others are so dense, so thick, that even Hubble cannot see through this region. And this is why we need to look in the infrared with a much more sensitive telescope like Webb. Webb can cover a much broader range of infrared light than Hubble can, and so it can look at these regions in different colors to gather an information about the various components of the dust. In particular, if we look at this region in the mid-infrared, the stars in the background disappear again, but the dust that initially was dark or transparent become all of a sudden bright. It starts to shine, and it becomes the protagonist of a scientific analysis. You can see from this image that the dust can have different colors because either a different temperature or a different composition. But by looking at these regions in the mid-infrared, we can start to understand what are the building blocks of the region of star formation. Finally, planets tend to be quite cold, and so they shine in the infrared. And because Webb is so sensitive, it will give us the opportunity to study planets that are forming or that are orbiting around other stars. In addition of its imaging capabilities, Webb is equipped with a series of instruments that allow it to disperse the light through all its colors. So they can create what is called the spectrum. Here you see an example of the optical spectrum that ranges from the violet down to the red. However, Webb is not going to see this part of the spectrum, but is going to see the infrared portion of the electromagnetic spectrum. As you can see in this image, in addition to see all the colors of the light, we can also observe a series of dark lines. These lines are caused by different chemical elements like carbon or oxygen, iron, that are present in the surface of a star or in the gas between the stars and our telescope. These chemical elements subtract a little bit of the radiation that is coming from the stars. And this is the reason why all of a sudden the light becomes dark. But they always remove this amount of light at always the same wavelength. So by measuring the position, the depth, and the broadening of this light, we can gather information about the chemical composition, the temperature, the surface gravity of the object that is emitting the light. And so we can really weight the amount of elements that are present on a star or on a planet. The infrared wavelengths that Webb can observe are also particularly interesting to understand how the life arrived on Earth, how Earth was able to develop life. In fact, in the near and mid-infrared, we start to see a series of complex molecules like water, methane, ammonia, methanol, And all these components are at the base of the formation of the amino acids that lead to the formation of life. So Webb is not only going to give us the building blocks for the formation of stars and planets, but is also going to show us how these complex molecules can arrive on rocky planets like Earth. So let's jump on the studies that Webb will do to understand the formation of stars and planets. We are going to invest a lot of time to understand how stars form, because this is one of the most important processes that happen on Earth. Immediately after the Big Bang, the universe was very dark, was very small, compact, and hot. It was filled with elemental particles that were able to collide with each other and create more complex elements, more complex particles like proton, neutron, and electron. And these elements together started to form the first, these particles together started to form the first elements like hydrogen, helium, and lithium. By the time we start to form lithium, however, the universe was already so vast, so expanded, and so cold that it wasn't able to create any other element. And for a while, it continued to expand as a dark cooling system, and nothing much more was happening. However, about 300,000 to 400,000 years after the Big Bang, gravity became the major force, and it started to pull back all this material that was running away. And in doing so, it started to form the first stars and galaxies. The first stars were very different from what we see today. They were thousands of times more massive than our sun. And on average, the universe was creating only very massive stars. In the interiors of these stars, the nuclear reaction that burn hydrogen into helium and other elements were running extremely fast. They were running at a furious rate, and new elements were going to be cooked inside these stars. However, these stars were also very unstable, and they were exploding like supernova very quickly, releasing into the universe a series of new elements that were not present before. This change in the chemical composition of the universe also changed forever the way that the universe evolved. First of all, for the first time, the universe was able to form Loma stars, stars that were even 10 times smaller than our sun. At the same time, even if it was not forming stars that were thousands of times more massive than our sun, it is still forming stars that are a few hundred times more massive than our sun. They can still explode as supernova and release more oxygen, carbon, and nitrogen in the universe. It can also create intermediate mass stars that are responsible for the release of more heavy elements like iron in the universe. And so for the first time, we start to have the condition that leads to the formation of planets. So understanding the process of star formation is very important to understand the evolution of the universe. However, if we look at nearby region of star formations, it's very hard to understand what's going on, because as soon as stars start to form, they start to change also the surrounding condition. In the image that you see here, that is the 30th anniversary image to celebrate Hubble operations, there is a large cluster of stars that formed in this region here. We cannot see this cluster because it's covered, it is hidden behind a thick wall of dust and gas. We can guess that there are stars, bright stars forming, because we see the reflected light in this region here. We also see that all the radiation and the energy released by the stars, by the massive stars that form in this region, has already started to disperse and pull away the material that was used by the stars to grow. And we have evidence of this phenomenon, for example, in the series of cavities that are present in the lower right side of the image. Clusters are environments that are very compact, where a multitude of stars are close to each other. This causes often a series of interaction and collision. And sometimes stars can be kicked off their parental clusters. This is what happened, for example, at NGC 2020 in the corner here. This star at birth was 60 to 80 solar masses, and it is rapidly running toward its death. It has already started to go through a series of violent expulsion and contraction, And as a consequence, it already lost part of its external envelope that you can see in this large ring of gas around the star. The star will continue to pulsate violently for a few other 1,000 years, and then it will explode as a supernova. In doing so, of course, it will going to blow away all the material around, and so it will further cancel the information that are associated to its birth. Star formation is not very frequent in the Milky Way. There are several regions that form Loma stars and some regions that form high mass stars. But very intense episode star formation are more frequent in nearby galaxies like the Large Magellanic Clouds. These galaxies are particularly interesting because they have regions where star formation is creating both very low mass stars and stars that are 60 to 100 times more massive than our sun. And they have a very different chemical composition. In fact, these galaxies are considerably less evolved than the Milky Way. And so they give us a glimpse of the process of star formation under conditions that resemble those that we would find in a much younger universe, where star formation was much more frequent, and star formation didn't have the time to already change the chemical composition of the gas. By looking at these regions, therefore, we can get a lot of information about the challenges that stars forms in the early universe, the stars faces in their formation in the early universe. As I mentioned before, star formation very quickly erase the initial condition that led to the formation of stars. And so we are not only looking at massive clusters in nearby galaxies, but we are also going to look with Webb at very dense dark clouds of dust that are in the center of our galaxy. These clouds are not forming stars yet, and they are so rich in dust that even with the Spitzer Space Telescope, we weren't able to see through them. However, Webb will be able to penetrate through these layers of dust and see what is in the background. And by doing that, by looking at how the light can travel in the infrared through these clouds, is going to gather a series of information about the structures and the dynamic of the dust and gas in these regions, and therefore characterize what are the conditions that will lead to the formation of stars in the future. Webb is also going to look at regions that are forming only low mass stars in our galaxies. These regions are considerably closer, and they give us a lot of information on the development of circumstellar and protoplanetary disks, the environments where planets like those in our solar system form. This is an example of a low mass star that is in our galaxy. We cannot see the star in this image because we are looking at it in the visible, and the star is completely hidden by its circumstellar disk that is completely hiding the star. We don't even see the disk because being made mainly out of dust looks dark in the optical. However, what we see from this image is that not all the material that is falling on the star remain on the surface of the star. Part of this material is pushed back into the space through very powerful and extended jets that can be as long as even few light years. The emission of the gas doesn't occur on a steady state, on a continuous flow, but there are multiple ejections with different velocities, and sometimes one ejection can hit one that was in front. And so we can see this development of multiple shocks. By studying the velocity with which these jets get out of the stars, and also by studying their chemical composition, we can see how the material gets reprocessed in this series of events. Hubble has shown us that there are several disks that will be visible for Webb, that Webb will be able to resolve. What you see here are examples of Proplid or protoplanetary disks that are surrounding stars in formation in the Orion Nebula. Again, we are looking at the nebula in the optical, and so the disks look dark because they are very dusty. However, if we move to the infrared and the microwaves, all of a sudden, the dust that is in these disks starts to shine. And so we can see that as a star evolves, as its disk also evolves, and it starts to develop a series of rings and cavities. So very young disks are uniformly filled, and then as small rocks and dust of grains start to collect dust, they grow and they create these cavities. And in doing so, eventually they lead to the formation of small planets that continue to grow around the star. We also see that the presence of other stars can affect the evolution of debris disk and protoplanetary disks. And we want to see how these can influence the formation of planets. For this reason, we are going to study the properties of protoplanetary disks in different environments, regions where there are only few stars and regions that are much more dense. Studying the structure of the disks at different ages is very important because it allows us to understand how complex molecules arrived, for example, on Earth. Hydrogen is very common on the surface of it's very common on the sun, is the most common element in the sun, but it is very rare on the Earth. And that is because hydrogen is very volatile and can fly away. However, hydrogen is very reactive with oxygen and carbon, and so it can create complex molecules that can coat the dusty grains that are forming the disks. These dusty grains, this coating, it's an icy form, and it can grow on the dusty grains, can lead to the formation of asteroids and comets, and it can fly through the protoplanetary disks and arrived on the planets, on the young planets. So study the chemical composition in the infrared at different wavelengths can tell us where the various elements form and how they move across the disks as the disks evolve. In addition, at looking at star-forming disks, Webb is also going to study planets that have already formed. Sorry, in addition to study protoplanetary disks, Webb is also going to study planets that already formed and how their light changes, for example, as how they affect the light of a star as they travel in front of a star. This motion is called transit, and we can see that the luminosity of a star changes as the planet travel in front of it or even in the back. Planets do not emit light by themselves, but they act as mirrors. So they can reflect the light that is coming from the star. When the planet is between us and the star, it shows us its dark side. But then as it moves backward, it starts to reflect more and more light from the star. If we look at a star in different filters, we can see how, for example, the planet changes in reflecting the star. There are also a series of planets that orbit around their stars at very high velocities in very close orbits. So in just a few hours or in a couple of days, they can complete their rotation around the star. This type of planets are in what is called a locked orbit, and they are always showing the same side to the star. This means that there are huge difference in temperature between the side that is always facing the star, and so it's always experience a day, and in the night side of the planet. Depending on how the temperature changes between the night and the day side of the star, we can gather a lot of information about the thickness of the atmosphere of the planet. We can first of all understand if there is an atmosphere around the planet. And also we can, by looking at different colors of the planet, we can gather the stratification of the atmosphere or information about the surface of the planet. We can even push our curiosity one step further and see what is the chemical composition of the atmosphere and really quantify how much oxygen or water or ammonia is present in the atmosphere of the planet. To do that, we are still going to take advantage of the transit of the planet in front of the star, but we are going to take, instead of an image, a spectrum. The atmosphere of the planet, exactly as the atmosphere of the Earth, is going to subtract a little bit of radiation from the sun And so on top of the spectrum of the star, we are going to see also the little narrow dark line that are caused by the presence of the atmosphere of the planet. So by comparing observations of the spectrum of the sun before the transit and of the star before the transit and during the transit, we can see what are the properties of the atmosphere of the planet. What you see here is an example of the atmosphere of an Earth-like planet, as it would look like for Webb. And this is how a Neptune-like planet would look like. And finally, this is the atmosphere of a hot Jupiter. As you can see, the shape of the line changes. And also some of the elements are present in the atmosphere of a planet, but they are not present in the atmosphere of another one. So by looking at the different properties of different stellar planetary atmosphere, we can gather information on their temperature, on their chemical composition, and on their surface gravities. And I'll stop here, and I thank everybody for your time with me. Bye.